Welcome back to the next segment on in situ chemical oxidation. In this segment, I'll be talking about some early lab results we collected, and then a little bit more about this idea of enhanced mass removal. When you inject an oxidant into a permanent well, the goal of the entire treatment process is to try and get the oxidant close to the non-aqueous phase or your target zone as you can. So in fact, if your goal is to go after non-aqueous phase liquid, then you need to have contact between the target, the non-aqueous phase liquid, and the oxidant. But the idea of this being a true contact sport is clearly a requirement. So the target spectrum then could be an observed bleb of apple in the field, or a lens where we have a pooled napple accumulation that sits on a capillary area. If you are fortunate enough to get the oxidant close by to the non-aqueous phase water interface, then the presence of the oxidant will cause the concentration profile off of the napple water interface to steepen. And by steepening that concentration profile, you actually will enhance the mass that is being removed from the non-aqueous phase liquid. And that is what I've called enhanced mass transfer. So our first experiments to explore this idea of enhanced mass transfer involved the placement of a PCE napple zone within a porous medium column structure, flushing the column from the bottom to the top, and at the effluent end, monitoring both the amount of oxidant that left the column and the effluent profile of PCE. So if we plot now then against time the profile of PCE from this column, here is what we get. So again, along the x-axis is time from the start of flushing. Along the y-axis is the PCE scale, a log scale. The red line indicates when the oxidant in the inflow was turned off. The green line is the control column, that one that did not see the oxidant. The purple one is the treatment column, that we flushed the oxidant until the red line. And one can quickly see that the effluent oxidant was suppressed in the effluent. Once the oxidant was removed from the inflow, there was a slight rebound in the concentration, and then the profile of the treatment column, or the behavior of the treatment column, is very close to the behavior of the control column. We also undertook the production of chloride, and based on the production of chloride, we're able to back calculate the amount of PCE that we destroyed. And based on the stoichiometry, we estimated at the peak here that the mass removal was increased by a factor of 6. So just by the presence of the oxidant, we were able to increase or destroy the amount of napple there by a factor of 6. So that then gave rise to an idea of enhanced mass transfer. So the idea of enhanced mass transfer then should occur for both blebs or blobs and for pools. So if we stare at a bleb or a blob and think about that as an isolated mass of non-aqueous phase liquid in some grains, and one can think about that length between the active flow channel and a blob, and call that length LC. And that length is, in my view, about the length of your pen. Then on the right-hand side here, we have an active channel that would be able to vary a slightly higher hydraulic conductivity pathway. And on the left side, we have the blob of non-aqueous phase. And we have on the active side, the oxidant would have to diffuse towards the blob, and on the blob side, the dissolved phase of PCE would have to diffuse outwards to the active channel. And that's called two-way diffusion profile, which is very similar to the profile that I showed before for this idea of enhanced mass transfer to occur. Well, you could write down the math of that. That process is not very hard to describe and is controlled by the type 2 Dom color number. That's the ratio of the reaction rate over the diffusion properties. So if we stare at some of these profiles, on this plot we have the length along the x-axis. On the left-hand side, I've plotted the concentration of PCE, and on the right-hand side, I've got the concentration of the oxidant. So if we stare at the start here at the profile of the PCE, so at the start we're here, as we allow the oxidant to diffuse inwards, the profile then steepens backwards until about 50 days the profile has reached a steady state. As the oxidant then propagates inwards, this interaction here now is the oxidation front, and that's where the highest production of chloride occurs. So if we stare at the steepening of this curve, we can then back calculate how much the mass removal rate has increased. So along the y-axis here is the enhancement. Along the x-axis is time. We start off at close to 1, and then as the oxidant propagates in towards the front, that will increase up to a steady state here of about 4.3. So that says that the most you'll ever will enhance this is 4.3 times what it is without the oxidant there. If you increase the concentration of the oxidant, so the one we had there was for a oxidant concentration of 1 gram per liter. If we increase that to upwards of 40, we could see an enhancement of about 66. But of note here, though, is that the length of time it took to get that. So to actually enhance to a factor of 4.3, based on these calculations, it says that the advective channel you would have to flush or have to have present there oxidant at the concentration there of 1 gram per liter for 50 days. So that concludes this segment on the early lab results and hopefully convey to you the idea of enhanced mass removal. In the next segment, I'll be speaking about the outcomes of some pilot scale experiments. That's all for now. Hope to see you again.